Hi, I'm Kevin Fu,
And I'm Kevin Chung.
and this is our 2020 Computer Systems Lab Senior Research Project, AutoPGN, Automating Chess Move Notation. So if you've ever watched a chess broadcast, you may have noticed that the players have something interesting to the sides of their chessboards. Clipboards with pens or pencils on top. The players notate the moves of the game in portable game notation, or PGN, on these clipboards as they play. They do this for two reasons. One, so that they can study the game afterwards, and two, so that they can verify the game was played correctly on both ends. However, those watching at home do not follow along on clipboards, but on a digital board to the side of the image. A human expert must be watching the video feed of the game and updating this digital board as the players play. However, in some broadcasts, as you might imagine, there is no human expert. For those less skilled at chess, such as, say, a computer science student who does not play chess regularly, this can be more challenging to follow than the digital board from before. Wouldn't it be better if the process of displaying a board and notating moves was automated? Well, with Hough transforms, we can detect straight lines in an image. And with convolutional neural networks, we can identify complex shapes, such as chess pieces, in an image. Our proposal is to combine these two technologies to create an automatic chess move notation transcriber. Here to talk about how we did that is my partner, Kevin Chung.
When first looking at this problem, one of the hardest things to do is figure out what is happening on the board in the first frame. This is because we have no prior knowledge of where the board is, what the pieces look like, or where the camera is, and we have to find that all from scratch. And the first step in this process is finding the board. Our algorithm is based off of research done by Chizhevsky et al. And a lot of the techniques in our algorithm are heavily influenced by theirs. So the first step in board detection is line detection. We need to find straight lines on the board, or in the image. Sorry. To do this, we first apply contrast-limited adaptive histogram equalization to the image. And what that does is it increases contrast in the image, allowing us to see very easily detect differences between white and black squares on the board. We do this with 3 different settings, and that allows us to handle a wider range of lighting setups. After we run Clahe, we then run a probabilistic Hough transform on each of the 3 images. We do a probabilistic Hough transform rather than just a normal Hough transform because a probabilistic Hough transform randomly samples points within the image and only processes those, significantly reducing the amount of computations necessary. The probabilistic Hough transform gives us a list of line segments that it has found in the image, and in the graphic on the slide you can see all of the line segments that it has found in this image. What our algorithm does after line detection is line linking. Line linking is the process of taking 2 similar line segments and making them form one long line. We want to do this because we don't want to have to handle with all these tiny little line segments. We want to handle with straight lines across the image. The way we figure out if 2 line segments are similar is we draw perpendiculars from the endpoints of each line segment to the other line segment that we're comparing it to. And if the sum of these perpendiculars is small enough, then we say these 2 lines are similar. In order to merge them, we take each line and we make it into a point cluster. We may space out points, let's say like 1 pixel apart along the line, and then we take the line of best fit of all of those points. This process results in some residual lines, as you can see in the diagram. For example, the 2 diagonal lines in the top left corner turn into that 1 diagonal line going straight down, but our algorithm will filter this out in the next steps. So after line linking, we need to find the lattice points of the board. Now a lattice point is defined as one of the inner intersections of the board, where there is a square on all 4 corners of the lattice point. It does not include the edge points. In order to detect lattice points, we take a very small area of the image around each potential lattice point, and we feed it to a convolutional neural network. The structure of that convolutional neural network, or CNN, is on the right. And that neural network will tell us whether or not it thinks each point is a lattice point. So why don't we count the edge points as lattice points? This is because the way we pre-process these small images, oftentimes an edge will look like some outside background noise, and our network will become confused because of that. Another reason is that the edges are often obscured. For example, in this image, on the right side, we can't see any of the edge points because they are being blocked by the white pieces. Another reason is that the edges vary from board to board. For example, this board on the outside has letters and numbers, but other boards won't have those letters or numbers, and sometimes boards will have a different texture or color on the outside, further confusing our network. After we find those lattice points, the next step is line filtering. We combine the line detection that we had from earlier and the lattice points that we just found, and we use that information together to sort or filter the lines out, find which lines are most likely to be the board edges. For our purposes, the board is defined as the outer 4 edges of the inner lattice point grid. So it's the 4 edges of the 6x6 grid on the inside of the chessboard. With line filtering, we also separate the lines into vertical and horizontal lines. This is because we know that the board is going to appear as a rectangle or almost a rectangle to the camera. So we know that the board has to be made up of 2 vertical lines and 2 horizontal lines, further reducing the amount of combinations we have to try to find the board. And the last step of all of this is actually finding the board. So what we do is we try every combination of 2 vertical and 2 horizontal lines, and we analyze them with a polyscore function. This polyscore function takes the distance between the centroids of our potential board and the lattice point cluster, the areas of each of those, and also it takes into account the distance of the inner lattice points to the edges of our potential board. And we run this polyscore function on every single board, and whichever 4 lines have the highest polyscore, we say is the most probable board. And the next step is piece detection, which Kevin Fu will talk about.
Okay, so piece detection. There are 2 main steps to piece detection. The first is segmenting the board, now that we've found the board in the image, segmenting the board into individual squares. And the second is identifying what pieces are on those squares. So for example, in the piece detection header slide, you can see small boxes drawn around each square. So for part 1 of this, segmenting the board, we first do something called pose estimation on the board. So from the board corners, we can use a method of estimating points in 3D space using camera reconstruction called solve-PMP Rensec. And so from the board corners, the 4 board corners alone, we can identify an approximate position for the entire 9x9 grid of points that the chessboard creates with its intersections. Also, from this, we can project upwards in the z-axis. And so from a flat 9x9 grid of points, we can also project upwards and to the center of each of those squares, as shown by the little vertical green lines in the middle image. This is done to estimate the approximate piece height, so we can cut off the square image at an appropriate size. And finally, with the approximate height and location of each square, we can construct bounding boxes around each of the squares. And that's shown in the right image in blue. So these are 3D bounding boxes of which we will take the front face of to identify the pieces on. One trick we do in between this step and actually identifying the pieces is normalizing the skew. So as you can see on the left here, the raw bounding boxes themselves are slightly tilted to one side or another, away from the center of the board. So you'll see the white bishop looks like a parallelogram but skewed to the left, and the white knight on the right looks like a parallelogram but skewed to the right. We can correct for this using something called a homography transform. So basically, there's a built-in computer vision library called OpenCV that calculates, that solves linear equations to find a homography matrix, which will transform points from a skewed parallelogram to a flat rectangle. And so we apply that to make sure all of our images are as similar as possible to make classifying the pieces on them simple. So you can see on the right, the left tilted bishop and the right tilted knight have both been corrected to be straight up and down vertically. Okay, after we correct for the images that we've sliced out of the board, we can put them into a CNN similar to the way we do lattice points. Again, here we introduce a small trick. So you can see on the very left is an image of a white knight on an edge square. It's in slightly poorer lighting condition than the last image that you saw. And so this is pretty common among videos. Not every video is going to look the same, have the same lighting conditions, camera angles, etc. So to correct for this, we introduce data augmentation that's shown in the middle. And you can see that there are 15 versions of the raw input on the left. And each of these versions has a slightly different randomized set of parameters, such as different cropping, different stretching or distortion, and slightly different exposure and brightness levels. And so from this is just a graphical representation. The computer obviously doesn't generate 15 of these. It just picks a random set of parameters. So let's say in this instance, it picks the image highlighted in green. There's a horizontal flip applied, and also a slight brightness decrease and slight cropping increase. So we can feed the augmented image into ResNet 152, which is a very powerful variant of a CNN. And specifically with ResNet 152, since it is a well-known, it was designed for the ImageNet competition, which is an image classification competition. So it already has weights pre-trained. Basically, that means it's already learned how to classify images. So all we need to do is transfer learn on top of that to make it better at classifying chess pieces. And so by feeding our augmented image into ResNet, we can get output confidences as shown on the right. So in this case, the sample would be 98% sure that it's a white knight. The model is 2% sure that it might be a white rook, and it's not actually 0% sure. It's like 0.005 or something, but it just doesn't show because rounding. And so the reason we need to data augment for ResNet is because the number of raw images that we're able to collect is very small, and the number of possible lighting conditions or different cropping variations is too much for us to possibly actually collect. So if you're familiar with machine learning, you'll know this, but the more data that we can provide the CNN, the better its results will be when predicting what piece is on the square. And on this slide, you can see two graphs showing the results of this transfer learning. So again, because we're transfer learning, it's a relatively short training period, only 10 epochs. And you can see that blue is representing the training data and orange is representing the testing data. So what that means is we split our data set up into two separate groups, one of which we transfer learn off of, and the other of which we can use to evaluate how well it's transfer learning and see how well our model is generalizing. In a few words, to see how well the data augmentation is working. So you can see that though the training accuracy starts off very low and the testing accuracy starts off above that, eventually they both converge to around 95% or greater. And a similar story for the model loss, but in reverse, because loss is equivalent to error. You can see that the testing data also is slightly below the training data. This is standard in machine learning, but it indicates a small flaw with our model that we will discuss later. And then here's another way of looking at the results of ResNet. So this is what we call a confusion matrix. The true label is shown in the vertical axis, and the predicted label is shown on the horizontal axis. And then the counts for each intersection are shown on the actual matrix itself. So basically, for a perfect model, every single number would be on the main diagonal, so from top left corner to bottom right. And as you can see in this matrix, most of the numbers are indeed on that main diagonal, but there are a few notable exceptions. For example, the intersection between Black Knight and Black King, Black Knight being the true label and Black King being the predicted label, is 13, meaning the neural network misclassifies 13 Black Knight images as Black King images. You'll also notice that the center square is very dark. That just means there were many more empty square correct classifications by the neural network. That's just due to the way our data set is constructed. Obviously, if you look at a chessboard, there's more empty squares than non-empty squares. Okay, so as you can imagine, ResNet 152 is a fancy sounding name, meaning the CNN has indeed 152 layers. And so this takes a lot of processing power. So one way we can shortcut the amount of images that the CNN actually has to process is by using the orthophoto. So to start with, we take the raw image, we run it through Clahe. I don't remember the acronym, but Kevin Chung described it. So we can use Clahe to increase the contrast, and then apply what we call canny edge detection to the Clahe image. And so this gives us a black and white representation of all of the edges of the chessboard. As you can see, though, it's quite fuzzy. Luckily, however, we also have the information of the board corners. So using the board corners, and again, the fact that the chessboard will appear as a parallelogram that's close to a rectangle to the camera, we can again run a homography transform, similar to how we unshifted the axes of each piece. We can use a homography transform to get a top-down perspective of the board. This was also from Chizhevsky et al. Their paper described this process. But basically, with the orthophoto, we can search the top roughly half region of each square. And if there are a significant number of candy pixels there, we can assume that that square may have a piece on it. So if you look at the center image, the green rectangles represent the search regions, and this is a top-down version of the canny image on the left. So as you'll see, all of the empty squares on the top are clearly empty because there's no canny pixels in them. Some of the empty squares on the bottom, however, are marked as potentially having a piece because there's a lot of noise in the image. And so this is why our CNN still has so many empty classifications in the confusion matrix. And so finally, using the process I just described, we can simply threshold for if there's more than, say, 100 candy pixels in this region, then we'll call it having a piece. And so the results of that are shown on the right. The yellow highlighted squares are scores that are marked as possibly non-empty. And so the final step of all of this for the first frame is to create a diagram to replace the human expert from the very, very start of this presentation. So with the process of board detection that Kevin Chung described and piece detection that I just explained, we get a string in standard algebraic notation, or SAN, where lowercase letters are black pieces, uppercase letters are white pieces, dashes are blank squares, and each piece is represented by the first letter of its name, except for knights, which are N's, because kings take K's. It took me a while to figure that out, but from this, we can query a website called jinchess.com, and it will generate a graphical representation of the board from this string, as you can see on the right of this slide. Okay, so after we get this diagram of the very first frame of a video or a live input, we have to handle every other frame after that, and Kevin Chung will be describing how we do that.
So the benefits and difficulties of processing all of the other frames after the first frame. The benefits are we now can track the points rather than find them from scratch. We know generally where they were before in the last frame, so we don't have to look too far to find them again in the next frame. We also have the advantage of chess logic. Since we know there are rules to this game and each piece can only move in a certain way, we can narrow down the possibilities of each piece in each square. We could say this square can't be a king because there's no possible way for a king to move here in one move. However, the difficulties with processing all the other frames are hand occlusion. When a player is making a move, their hand will almost certainly occlude the pieces on the board and also the lines on the board, making it much harder to process those frames. We need to figure out a way to throw out those frames. Another difficulty is real-time processing. The whole process for a single frame currently takes about 20 seconds on my MacBook Pro. So this is clearly unrealistic for what we want in a real-time situation. And the last difficulty is detecting when a move has been made. As I mentioned earlier, when a player is making a move, their hand will be blocking a lot of the pieces and the lines. So we want to throw out those frames and not actually process those. We only want to process frames where there is no occlusion on the board. So the first thing we do is tracking, as I was speaking about before. To do this, we use the Lucas-Canade method to calculate optical flow. What this method does is it estimates the trajectory of points in a video by taking information from the previous frames and predicting where they will go. It assumes that these points don't move too far and that the camera has a semi-smooth trajectory as well. In the graphic, you can see all of the points are being perfectly tracked as the camera is moving around the board. And this is what we use. So this is what we use to shortcut having to recalculate all of the board detection stuff over and over again. To compare the efficiency of these algorithms, our board detection method takes about 15 seconds on a regular laptop, whereas this takes a 50th of a second. So this is much more optimal for real-time processing. Now the next technique we use is heat mapping, and this actually tackles all three difficulties that I mentioned before. What the process of heat mapping is it's looking at the color change of each square from frame to frame. The way we do this is we find each pixel in the previous frame, we find the corresponding pixel in the next frame, and we subtract them and find the difference. We then take the average of all of the differences in each square, giving us an 8x8 grid of average color differences. Now, one of the difficulties with this technique is that it is extremely sensitive to lighting. For example, in the two images in the middle of the diagrams right there, where there's just showing the knight and the empty square, you can see that the square behind the knight suddenly has a shadow in it in the next frame. And our algorithm sees that as a significant color change. Now, the first thing we could do with this color change is if a move is made, we can see which squares have significant color change. The two frames up top, that heat map is shown in the picture at the bottom, and the bright squares are the areas of significant color change. Now, piece classification, as Kevin Fu mentioned before, is a very long process, and we shortcutted that with the orthophoto. We can further shortcut that with heat mapping by only looking at the squares that have significant color change. We don't have to process the ones that don't change because we can assume that the pieces didn't move because the color didn't change very much. So we look at the heat map, we cross-reference that with the orthophoto, and then we process those squares. So heat mapping also tackles the problem of hand occlusion. When someone's hand enters the image, as shown in the images below, the heat map suddenly becomes very, very noisy. And it is very easy to detect that this is not a piece move. This is not one piece moving from one square to the other. This is something else. We don't want to process these frames. So we only consider the calm frames. Now with these calm frames, we have something that we like to call calm streaks or calm intervals. Within a calm interval, because there isn't much color change or much noise, we know that nothing is happening on the board. So we only want to look at the first frame of every calm interval to reduce the amount of times we have to run this whole process. So a real world example would be if somebody were to make a move, then move their hand out of the image, that would then start a calm streak until their hand came back into the image. And as I said before, we only want to process the first frame of that. With that calm streak, we want to ignore insignificant noise of maybe 1 to 2 frames. This is because maybe the light flickers a bit, or maybe even like a bug flies through the image. We don't want to have it restart the calm streak because 1 to 2 frames is not enough time for a piece to have moved on the board. So we don't actually want to say that is a new streak. We want to say that that noise does not break the streak or interval. Now, one situation that comes up a lot is that a player will put their hand on a piece and then leave it there to think about it. With the heat mapping method from frame to frame, this will now look like it is a new calm streak because nothing is changing. The player's hand is sitting still on the piece. In order to tackle this, we compare a potential calm frame, in this case the frame where the player's hand is sitting on the piece, to our previous known calm frame, the board without any occlusion. And then we look for a hand again. If we do see a hand, we throw out that frame again and we wait for another calm streak to start and then continue the process. So on top of all of that, we have chess logic. And this improves the accuracy of piece classification by a significant margin. The way we do chess logic is we do it on a square by square basis. In the image on the left, we can see square number 18. There are only 3 possible pieces that can exist in that square in the next frame. The black pawn can remain there, it can be captured by the white pawn, or it can be captured by the white queen. So if we see, if our network classifies any other piece there, we know that it's wrong, or that the player has made an illegal move. But at the right now, we assume that the player is each player is making legal moves. The example on the right is a similar thing. The square number 26 can only contain an empty square, the black pawn, the black knight, the white bishop, the white knight, or the white queen. Now, if the network classifies the piece in that square as something that isn't possible, for example, on the left side, let's say it classifies square number 18 as a black knight. We will then go down the list of confidences in order and find the next highest confidence that is a valid move. So maybe after the black knight is now a black pawn, which has a lower confidence, but from chess logic we know that it can't be a black knight, so then we say that is a black pawn.
Okay, one last thing on the chess logic is because we're assuming valid actual chess games, we can say safely that each side has at most and at least 1 king. So by using that logic in a similar way to the way we check the confidences of every square, we can check globally for the highest confidence black king and the highest confidence white king and assign those 2 pieces as definitively the kings. And then similar to what Kevin Chung said, we can then strike out a black king or a white king being a possibility for any other square. Oh, it is my turn. So finally, after all this process of board detection, piece detection, and applying that to several frames of a video, we can transcribe the actual moves. So I realize that not everyone might be familiar with portable game notation. So I'm opening up a free chess site called leechess.org to demonstrate. So you can see here is the standard starting position of a chess game. if I move the knight, the white knight, let's say here, you can see the white knight moved from B1 to C3, and then down in the bottom it says 1 NC3. So it uses standard algebraic notation, or SAN notation, at the start of every PGN move. So here, capital N, meaning white knight, and then also the square that it moved to, C3. So crucially, you'll notice that it doesn't actually include information on where the piece moved from, because PGN was designed not to be interpreted by computers, but to be played out in sequence by human players, or to be written down as human players are playing very quickly. So it's much easier just to write down the end square of every piece. So if I make another move, you can see another quirk about PGN for speed is that pawns are not indicated. So here, the PGN move down below just says D5 because it's implied that a pawn moved if there's no letter indicated. And then the final thing to note about PGN for most use cases is this move. So that's knight takes on D5, or capital N X D5, as shown below. So that's pretty self-explanatory. It's the same thing. The piece first, then captures if there's a capture, then the end square. So this actually is a bit challenging from a programming standpoint because based on the individual states of the board that we were able to extract from the video, we have to figure out where the end squares were, if there was any piece captured, and if the move was legal. So we do this in a similar way to chess logic. Chronologically, we actually did this part first and then did chess logic afterward, but the principle is exactly the same. So we can check the differences, much like heat mapping, we can check the differences between board states and figure out which square has changed. Then we can figure out which square was the end square by checking all possible moves of the piece that is in one of those different squares and seeing if the previous frame had a color difference on one of those squares. So let me explain. This knight, we know that it moved from C3, but if we're just given the end and the start position, we can see, so this is the starting position, this is the ending position. From the end position, we know that the knight must have come from one of these locations, because that's how knights move. So looking at these 6 squares, if we go back one frame, we see that the knight did in fact come from one of these 6 squares. So we can assume that was its starting location, this is the ending location, and now we also know from the starting that it captured a black pawn. So we include all of that information and get knight takes d5. Okay, so putting that all together, we can show you a live demonstration. Let me pull that up real quick.
While Kevin Fu is pulling that up, just a quick note about Lichess. Lichess is not part of our project. It is simply for demonstration of PGN. We have our own software that finds the PGN from one board state to the next board state.
Unfortunately, we had to code it ourselves. So what you're seeing right now in the top window is a pre-recorded video. It's playing back at real time, so all of our processing is being done in live speed, but we just don't have a live video feed because the only option we found was a $1 app called IP Camera, and that works by broadcasting video through the Wi-Fi, and we found issues with latency, so we just pre-recorded a video that you're seeing now. So you'll see on the bottom is the graphical representation of the chessboard to replace the human expert that needs to watch the game and actually change the digital board. And then on the very left, in black and white text that I can zoom in, whoops, forgot about that, you'll see the portable game notation as well as a printed out version of the same graphic diagram. So right now, the first 5 moves of the game have been played. You'll see G3, meaning white pawn to G3, knight F6, meaning black knight to F6, and etc.
So while this video is playing, you will notice sometimes the video slows down and then speeds up in some areas. This is because when someone's hand is in the board, we don't want to actually process those frames. We're just throwing those ones out. and we assume that the board does not move very far while the person's hand is occluding the board. We don't run tracking either because if someone's hand is where a point used to be, it will start tracking their hand rather than the actual corner on the board, and we don't want to mess that up. So we just throw all those frames out, and you will see the video speed up very slightly when someone's hand's in the image, and then slow down just a bit when their hand leaves.
So right now, both players have just castled. That's indicated with the 0-0 in the PGN on the bottom left. This video is not a full chess game. We would not make you sit through a whole 10 minutes of me moving pieces by myself. This is just the first, I think, 7 or 8 moves, approximately a minute of video, to demonstrate the full process on a variety of situations. Yeah, there's nothing much to comment on here, other than the fact that it's working.
As you can imagine, having something like this would have many applications further than just a chess broadcast. For example, we had the idea you'd be able to set up real boards for 2 different players in 2 different locations, and over Wi-Fi you could play online chess but with a real board. Another application is using a real board to teach someone chess. You would have a chess AI look at the current board state, and it could play audio from the computer, telling the player what moves are good and what moves are bad in each situation.
From a more personal standpoint, one of our SysLab directors is an amateur chess player, and he would use a system like this to maybe keep track of his casual games. So you don't have to be like a professional player to want to remember how chess games went. In fact, for pros, oftentimes they can memorize entire games, which is just unfeasible for a casual player. So having something like this means that they could just have the list of moves and they could play it back anytime they want. So we're about nearing the end of the video right now. I think these are the last 2 moves. White pawn moves up to e5. And in a moment here, we'll see black pawn captures. I think I'm wrong. I think there are a few more moves. What else? Kevin, do you have anything? Oh, thank God. Okay, it's saving the file, as you can see. So it says saving PGN file to this file path. This is just the input that I gave it to save to. You can see it transcribed 15 moves there. I think in a second when it closes, there we go. I will open the PGN file. And you can see on this very small font that I will zoom in, you can see that it just saves the output log as printed here. I can copy that, go back to Lichess, paste it there, click import PGN, and all of a sudden, all of the moves from that game that you just saw are in Lichess. So I can scroll the right arrow, you'll see the exact same moves played. If you don't have them memorized, just rewind a little. We promise, not faking. But yeah, there's the pawn move, and that's the end of the video. Okay, so as you can imagine, our software doesn't work perfectly in every use case, and so Kevin Chung is going to talk about a few future improvements.
So the first improvement that we wanted to speak about is calm frame detection. The calm frames being the frames that don't have any occlusion in them. Oftentimes, we will see our software label a frame where someone's hand's in the image as a calm frame, and that's because right now we're using a pretty brittle threshold rather than a more robust method. So if someone were to come along and develop a more robust method, it would significantly improve this calm frame detection and improve all the mistakes that follow after you label a not calm frame as calm.
So the second issue listed here is the stability of the ResNet model used to classify pieces. So as you can see on the graphic on the right, that's clearly a black pawn, but it recognizes it as a black king, with black pawn being listed as a distant second with 30% confidence. So this is because, again, lack of training data. So the data augmentation that we implemented helps, but the fact is that the training data set is small and contains many duplicate images. So the model is very sensitive to the angle of the camera, and thus the angle of the pieces, the lighting of the board and pieces, and also the color of the sets itself. Much like comp frame detection, if this piece of our project were to be improved upon in the future, then the overall results would be significantly better. So the third and final improvement that we think is most significant to our project is the depth of chess logic. So as Kevin Chung explained earlier, we go on a square by square basis and check all the possible pieces that could be on a square after a move is played. This, however, means that we must account for the probability, or the possibility, rather, of the piece moving, which means that the square that it moved from would be empty. And so for every single piece on the board, we have to include the possibility that it becomes empty in the next move. However, this leads to problems if the ResNet model incorrectly classifies a piece that has not moved as an empty square. Because of the way we're doing the checking on a square by square basis, this will fall through our chess logic filters. If you think about it on, a chess game standpoint, obviously, if the pawn has moved, then it must have moved to a square. And if our model contradicts itself and it identifies all the squares that the pawn could have moved to as empty as well, then there's a conflict there that we're not checking for currently. So these are the three improvements that we think could be made on our project in the future to increase its performance. And with that, thank you for listening to our presentation.
If you guys have any questions, feel free to contact us at either of our Gmails listed on the slide below.